All right, welcome everyone. So in this video, we are going to continue working with Markov chains, and let's see how we can make long-term predictions with Markov chains. So for example, why might we want to make predictions far off into the future? Well, let's say based on migration patterns for a certain species in a certain ecosystem, we want to make a long-term prediction way out into the future for what is the predicted population for this species. Is this species going to die out? Is this species population going to grow without bound? Is it going to approach some equilibrium quantity? The same for infection rates, and as we model disease spread, we might want to know, as this disease progresses out into far off into the future, what is the prediction for the total number of people that might become infected? And so if we would like to make predictions far off into the future, then what we would like to do is calculate what happens when I multiply our initial state vector x0 by the transition matrix P k times over for a large value of k. And so we've seen in our work with eigenvalues and eigenvectors that if we can diagonalize this matrix P, then that's going to help save a bunch of time in exponentiating this matrix. And what's really useful at figuring out whether we can and how to diagonalize a matrix is looking at the eigenvalues and the eigenvectors of that matrix. So here is a nice theorem about one such eigenvalue and eigenvector for any transition matrix P. So transition matrices, these are special type of matrix called a stochastic matrix. And recall that a stochastic matrix has a property that the entries in every column in the matrix add up to 1. So every column in the matrix is a probability vector. So this theorem is saying that if P is a stochastic matrix, then 1 is going to be an eigenvalue of matrix P. So any transition matrix has 1 as an eigenvalue. So let's take a look at why this statement is true. So let's start with a matrix P, which is stochastic. Then let's consider the transpose of this matrix. P with a superscript of T means transpose of P. So we're going to flip the rows and columns of matrix P in order to get the transpose. And so since the columns of matrix P added up to 1, then what we know is that each row in the transpose of matrix P must add up to 1. So now let's consider the following vector that I'll denote E. So E is a vector that has all ones in it. So let me just write that over here. And we have n different entries in E. So let's consider what happens when we take this matrix P transpose and multiply it by this vector E that consists of all ones. So for the first entry in what comes out when we take this product, I would take P11 times 1 plus P21 times 1 plus P31 times 1 all the way out to Pn1 times 1 and add all of them up. So basically, we're going to just add up all of the entries in row 1 to get the first entry in the resulting product. And this is going to be the same for all of the other entries for the resulting product that we get. And so now this first entry, which is the sum of all of the entries in the first row of P transpose, recall that this matrix is not P, but P transpose. So adding up all of these entries in P transpose is equivalent to adding up all of the entries in column 1 of P. So P was a stochastic matrix, so adding up all of the entries in column 1 of the original matrix P is going to give us 1. So I know that this entry actually simplifies to 1, as does this one, as does this one, as does all of them, because P is a stochastic matrix. So in other words, what we get, the vector that we get when I multiply the transpose of P times this matrix E of all ones, we get a resulting vector which has all ones. So in other words, we get the vector E back. So what I can see here is that this vector E is a eigenvector of P transpose corresponding to the eigenvalue of 1. So now I can see two things here, that 1 is an eigenvalue of any stochastic matrix. I guess I should be careful. 1 is an eigenvalue of the transpose of any stochastic matrix, and we've proven that matrix P and P transpose have the same eigenvalues. So if 1 is an eigenvalue for matrix P transpose, then I know that 1 is an eigenvalue for our matrix P, and we have this corresponding eigenvector for P transpose, which was this vector E of all ones. So this proves the theorem that if P is any stochastic matrix, then we know that 1 is an eigenvalue of P.